Okay, so for the first part, we're looking at this inductance right here. We have A, which has higher voltage, and this side is B, which has lower voltage. So the overall current is going to the left. But to counteract this current, there's going to be an induced current in the inductance that is going to go from low to high voltage. Therefore, to counteract the increasing current that's going to the left. So we know that the current overall is increasing because there is an induced current in the inductance, and that's the answer.
So the magnetic field that was initially provided is into the page and it's increasing. So the current induced in this loop is going to create a magnetic field to counteract that because it's increasing. So the induced magnetic field is out of the page. Use the right-hand rule to find the direction of the current in the loop with this induced field. And so you put your finger out of the page, your fingers curl in the direction of induced current, which is counterclockwise. And so the electric field induced at points on the loop is going to be tangent to this current. And so at the top point, it is going straight to the left. Here it is going down and to the right, and here it's going up and to the right.
For part C, we are looking at an electromagnetic wave propagating through point P. The green is the electric field vectors, and the blue is the magnetic field vectors. And we can tell that it's propagating in this direction by this equation. So the electric field, by the right-hand rule, will be our thumb. The magnetic field will be our pointer finger, as we can see here, which means that the pointing vector is going in this direction, this way, across the x-axis. And for the magnitude of the magnetic field, we are given that the electric field max is 30 volts per meter. And by this equation, we can find that the max of the magnetic field is 1 times 10 to the negative 7th Teslas.
So for this question, we're supposed to find the magnitude and direction of the pointing vector at time t equals 0. And so this is the equation for the pointing vector. S equals 1 over mu naught times E cross B. And so if you're trying to find the magnitude, it would just be 1 over mu naught EB sine theta. And so when you plug that in here, because at time t equals 0, they're both at a max. So we can plug in the values E max and B max for E and B. And then also, since the electric field and magnetic field will always be perpendicular, this will always be sine of 90 degrees, so sine of theta will always be 1. And so when you plug it in, 30 times 1 times 10 to the negative 7 over mu naught, you get 2.38 watts per meter squared. And we know that it's going to be going in the I direction because the pointing vector always points in the direction of wave propagation. Or you could do E cross B at any given point, like E cross B, your thumb points to the right.